This is a video about electric field superposition. And when you study electric fields, often after you get past point charges, a bulk of the class will be about electric field superposition. And in the case that I have sort of drawn on the whiteboard right here, here's a case where you have two charges, a positive charge up here and a negative charge up here, and we see their respective field lines. The positive charge electric field lines are in green, and the electric field lines due to the negative charge are in blue. And one of the questions that you might be asked, say, in a problem is, what is the electric field at some point in space, say a point like right here or right here or right here, because of the two charges. And the only way to find what the electric field is at one of these points or any point in space around these two charges is by doing a superposition of the electric field of the two charges. So the electric field at this point has a contribution due to the positive charge and a contribution due to the negative charge. And in a problem to find, say, the total electric field at this point, it'd be your job to do a superposition of the electric field due to the positive charge at this point and a negative charge at this point to find the total electric field. And there's a previous video to show a few examples of this. This is a dipole right here. But the issue with the dipole, or not so much a problem, but the issue is that these are discrete objects right here. And by discrete, I mean you can usually count the charges that are involved. In this case, we have two charges, so we have to add up the electric field due to two charges. You might have charges on the edges of a square like this, maybe a positive charge here, a negative here, and a positive here, and you might be asked to find the electric field at this point. This is another discrete problem here because we have 1, 2, 3 charges. And again, the problem really is just a matter of finding the electric field due to the negative charge and this positive charge and that positive charge. Doing a big vector addition problem, do a big vector addition problem at this point to find out what that field is going to be. Those are discrete cases. And in a discrete case, usually the electric field is just, the vector is just sort of a sum of the individual electric field due to some charges. And typically in textbook problems, you're never going to have more than about 2 or 3 other charges because it just gets too cumbersome. But whenever you see a sum like this, that sort of refers to the idea of something being discrete. In other words, you can count the number of charges in a given problem. But where the class actually starts to get kind of difficult, and this is probably going to be the first very extremely challenging part of a class like this, is where you have continuous objects. Now, you'd like the electric field due to a continuous object, and a continuous object has some very sort of unusual properties that make the problems a bit more difficult. So it'd be a problem like this. Suppose you had a charged rod like this that went all the way across the x-axis like this. Here's that rod right here. And suppose you wanted the electric field right here at this point above it. And just to set up a little bit of geometry here, we'll draw a Cartesian coordinate system on the rod like this and just place it along the x-axis, and we'll make it even symmetrical. We'll say this point here is a position L over 2, and this point over here is a distance minus L over 2. So this is a rod that has a total length of L, and furthermore, we'll just sort of claim or say that the rod has been charged with a bunch of positive charges, so it's a positively charged rod, something like this. Just draw as many positive charges as we sort of comfortably can on there, and ask the same question that we asked in the discrete cases: what is the electric field right here at this point? Okay, and this is a continuous object, so this is a rod, like something like you could hold in your hand, like a wooden dowel or a piece of glass that's been rubbed by fur and it's been positively charged. I think you'd have to agree that there will be an electric field at this point because there's a bunch of positive charges around, and one thing we know about charges is that they fill all of space around them with electric field lines. So what would it be for a line like this? Lots of things to consider here. The first thing is that, how would I even begin to do this here? Because if you look at the picture sort of very carefully, what we have here is we have, well, just as well as I could draw it. For instance, I have a positive charge right here, which is going to make an electric field sort of through that point. Now, this positive charge alone, this one little one that I've drawn right here, causes electric field lines to exist in all space around it, but there is one electric field line that goes through this point. There it is. This one causes an electric field line through the point. This one causes an electric field through the point. This one does over here too. So does this one. This one does over here too, and this one does over here. So you can see what's sort of happening here. So in order to find the electric field because of all these charges in this rod, you have to account for the electric field due to every positive charge in the rod. You can sort of see what a big superposition mess we have going up here. I mean, if I was going to do a discrete sum here, I'd easily have the sum of probably like 20 different charges in here. But what I've done is very imprecise. I mean, I don't really know if there's this many charges in here, if this is actually what they look like, or at least to the resolution of my pen, I don't know there isn't another charge between those two, and another one in there, and another one in there. And even the ones that I pack in there might be even another one in there, and another one in there. And even between those, just more. I mean, this thing could just be filled with charges like that. If I could really paint them on there, there'd just be millions and millions of charges in there, or billions even, and they're just all packed on. And you have to add the contribution of every one of these charges through that point right there in order to find what the electric field is. So it gets to be kind of a problem here. But the problem is you just have to approach it differently. But in terms of this being a discrete problem, you would say no way. There is no way you're going to be able to sum all those charges together anymore because there are just too many of them. They're too tightly packed. So what has to happen then is you have to start using some calculus in here. So the sum that you would normally use for a discrete case, in other words, adding the 2 or 3 charges that you'd have in a problem of a square or a triangle or a dipole or something like that, now has to become an integral, a calculus integral, because the charges are so tightly packed together that you can't possibly sum over them anymore. But what we know about calculus is that when we start talking about things being differentially close or appearing to have infinite extent or something, the sum has to become an integral, and we have to proceed that way with some calculus. So that's what this problem's about here, is we'll try to work on it a bit here, get some of the machinery going, and we'll actually do the problem for finding an electric field above a charged line like that. So just a couple things to consider here as long as we're talking about the discrete versus continuous. Let's do a little bit of discrete stuff over here. We know, for instance, that the electric field due to a discrete object is kq over r squared. That's the famous point charge equation that we have. And if we have more than one point charge, of course, we can add the electric field due to one point charge plus the electric field due to another point charge. And I guess to be totally correct, I should put vectors over this line and make this into a vector here, because actually what we're doing is a vector addition. So often the challenge in these discrete problems here is in doing the vector addition here, where we have to find, say, the x and y components and so on. But the point is that in the discrete case here, we have this sum in here. So this line like this sum here is exactly where that sigma comes from in here. The capital sigma meaning sum. So you add them together, and lo and behold, your answer usually comes out. But when we go to the continuous case over here, we have to take a different approach, because as we're saying, in this rod here, there are just too many charges to add together in a discrete sum. We must use an integral. And as you know, an integral really, what is an integral really? It's just an infinite sum. That's one of the premises of calculus right there. And so that's we'll just sort of go with it here. In fact, that's where the integral sign comes from here. If you spell out the word sum, you just take an S and make it nice and long. It looks like an integral, and that's where that notation even came from. So what we have to do over here is we can't really use E as kq over r squared anymore, because that only works for discrete things. But what we know from calculus is that we can start forming differential forms of these things. In fact, what we do is we go up here and say, look, there's so many charges crammed into this rod right here, I can't possibly count them all. But what I can do is I can try to discretize the problem and prepare it for an application of calculus. And the way I'll do that then is I'll come over and go, you know what I'm going to do instead? So I'm going to take a slice of this rod right here, a very thin slice of it. And the slice of this rod here is going to be so thin that I'm going to call its width dx. So I'm not even going to call it a width x or L or anything. I'm going to slice it to a dx. And one thing we know about differentials, they're extremely small. Remember, dx is sort of what happens when you take an x and you let the limit of something go to 0. That's sort of where, let's say, a limit goes to 0 here. That's what a dx actually is. So what we're doing is we're taking this rod with all those positive charges packed on there, and we're taking a very, very thin slice of it here and calling it a width dx. So what's in this slice here is really hard to say, but we've gone so small in the calculus sense that we can actually see maybe one of the contributing positive charges. The dx is smaller than the atom, it's smaller than the nucleus, it's smaller than anything you can possibly imagine, because remember, the dx comes from a limit when some variable goes to 0. So it's an extremely small slice of this rod here, but that's exactly what we need to get in there and see exactly how much charge is in there. So typically for a rod like this here, we don't even try to address how much charge is in there, but it'll have some parameter called lambda here, which is the charge density, which are how many coulombs per unit meter are packed into the rod. So this is a density right here, a charge density. And often the textbook use lambda for this type of thing here. So that's the sort of regime we have to get in for the calculus, is we take a very thin slice, smaller than any atom itself, because the limit of something goes to 0. And also, just to get a handle on how much charge we might expect as we get into there to that subatomic, subnuclear size of the material that it's made out of here, we'll have something called a charge density, which always tells us how many coulombs per unit meter are in there. Very high number, very low number, what? We'll see how we'll use that in just a minute. But these two green things, the dx and the lambda, those are the key things to getting a handle on this problem here. And because this is just too big, we can't possibly have a q right there. The e is going to become a de, and it's going to be k times dq over r squared. So this is sort of the formula that we'll start with here. We won't have the e anymore, but we can have a de in there. Where does the dq come from? It comes directly from the dx up here. So we have a very small slice of this rod here. The question might be, well, how much charge is in one of those slices there? And it comes from a pretty simple relation here that says that dq is that charge density lambda times dx. So you can just sort of remember this or look at the units here, that if lambda has units of coulombs per meter and dx has units of length, like meters here, then you can see that dq would just be in coulombs. Remember, this has units of coulombs per meter, and if you multiply it by meter, the meters cancel here, and you're just left with coulombs, which is the proper unit of some charge, even though it's a small amount of charge, the dq in there. So, one more time, dq is lambda dx. If dx has units of meters, lambda has units of coulombs per meter, then the meters cancel here, and you see the dq has units of charge like that. So, instead of just trying to figure out how much charge in there, we extract that global parameter lambda, which is the charge density, and multiply by the width of that small slice, and that gives us the q, the dq that's in that slice. So the dE then is going to be k times dq, oops, I didn't mean to write that, k times lambda dx over r squared. That's going to be the differential electric field. So this is a very important result here, and is often how these problems start, at least for the line, it's going to start like this here. So this is the differential E field, and it's produced by the differential charge, the differential Q, in the differential sliver dx. So a lot of differentials in there, but that's exactly what this means here. Let's just read it one more time. This dE here is the differential electric field produced by the differential Q that's found in the differential sliver dx. This is just the big time application of calculus here. You take the sliver, very small, narrow sliver, so small that it's a limited approach to zero, and you ask the question, how much charge could possibly be contained in that sliver? Well, that's a differential Q, a dq. And if whenever you have a charge, no matter how small, it will produce an electric field. So once again, just like in the discrete case right here, the Q produced the E. That's a fact. An amount of charge will produce an electric field. And in this case, in the differential case, a charge still produces an electric field, but a very small amount of charge produces a very small field. So a macroscopic Q produces a macroscopic E. Here, a differential Q, a dq, produces a differential electric field, dE. So you start out with this sort of analysis right here with the calculus, and now, and only now, can you begin to apply it to a continuous object. So what we'll do then is stay tuned for the next video where we'll actually apply this type of idea right here, and this differential idea here, to a few systems, starting with the line of charge.